Can you distinguish when you look at a molecule the difference between an ionic bond and a covalent bond? So if I draw hydrochloric acid, HCl, is that a covalent bond or an ionic? I saw a lot of you shake your head that you knew what a covalent bond was or an ionic bond. Here's your chance. What is it? That's a covalent bond. Because we know that this bond right here represents what? Hydrogen comes in with one electron, and chlorine comes in with that one electron. But we know that chlorine also has those those valence electrons or lone pairs. And we remembered that hydrogen, what? Needs 2 electrons, so it shares the one from the chlorine to get its 2. And then chlorine's going to share to get its octet, or its 8, right? So that line right there, that covalent bond represents that there's 2 electrons there. That's kind of holding these atoms together. So what we want to understand, though, is this idea that there's an electron there. We think of electrons as particles, but when we deal with chemical bonding, we have to think about it as a wave function. You know, the sine function or cosine function, just up and down, it's just a wave. So that particle, or that electron, behaves as a wave, and the way that we represent that electron is a wave function. And the way I think you've been taught is that you have these orbitals, right? A 1s orbital or a 2p orbital. And I think your instructors would say, hey, we take an electron and stick it into that orbital, kind of like just sticking it into a box, an object in a box. That is not true. The orbital that you guys have been taught and you learned is actually the electron. The electron is being described by that orbital, okay, where it's located in three-dimensional space. So what I want to kind of get you to think of, like, this one electron is in what? A 1s orbital, okay? And sometimes I'm going to show it as an orbital, like that sphere, and then I can stick the electron in there, okay? But we have to understand that we have different types of orbitals. We have 1s. What's after 1s? 2s. After 2s, 2p. Okay? So s orbitals are a sphere, and what do p orbitals look like? Just a dumbbell looking shape, right? And they have a phase, a negative and a positive phase. So if we take a look at, I forgot my model. So I want to take a look at a molecule called methane. Darn it. There we go. So let's take a look at methane, which is CH4, right? So when we take a look at carbon, the carbon atom in its ground state, how can we figure out how many electrons it has? Well, the first thing is we can go to the periodic table and zoom in on carbon right there. How many total electrons does carbon have just by looking at that periodic table? It has 6 protons, so it has 6 electrons. But how many valence electrons does it have? You look at the group number. And we see that that's a 4. Okay? So 4 valence electrons for carbon, silicon, and so forth. If we take a look at nitrogen, how many valence electrons does nitrogen have? It has 5, and so forth. Okay? So that's how we're going to know how many valence electrons we have. So if we go and take a look at the electron configuration of carbon, can we draw that? And carbon has a 1s, a 2s, and a 2p. And there's 2 electrons, 3, 4, 5, and 6. So that's the ground state configuration of carbon. And if we take a look at carbon, and those are the valence electrons right there, we have 2 electrons that are paired, and we have 1 electron unpaired and another unpaired. Okay? When we come back up to hydrochloric acid, do you see how 1 electron and 1 electron, when they get shared between 2 species, it forms that covalent bond? Just like that. Well, same thing with carbon. We could bring a hydrogen with its electron and a hydrogen with an electron. So those like that, and those could share with one another, right? So we could have a molecule that looks like this. Like so. But when we go to nature and look at carbon atoms, that's not what we see. That carbon atom that I just described in its ground state can only form 2 bonds. But we know that carbon wants to form 4 bonds. Always 4. So how does it form 4 bonds? Question or comment?
Comment.
Okay.
Does the electrons from the 2s orbital go to the 2p orbital, so it has 4 areas of bonding?
No, it does not do that. But that's a good thought.
I remember.
That's a good thought. Okay. So if it forms 4 bonds, we know this from nature, then maybe it would look something like this. Right? Carbon with 4 electrons there to form 4 bonds. And so we have seen the molecule called methane before. Carbon with 4 hydrogens attached to it, methane like that. Now, I know this is a small model here, so my apologies. Just see my model here. I'm trying to make it just look like what I just drew on my iPad. You see that? Do you see how all the hydrogens are in the same plane? It's completely flat. That's not how it works. That's not what we see in nature. Our carbon atom is tetrahedral. Remember that word, the tetrahedral geometry? So a tetrahedral geometry looks like this. We have a carbon atom with a hydrogen and a hydrogen in the same plane. And then we have a wedged hydrogen and a dashed hydrogen like that. Now, what does that look like? And my apologies, I forgot to bring my big model. So this will have to do. Okay. Now this carbon atom, or this methane molecule, as I put it on my iPad here, can't see it very well, but do you see how it's not flat like this guy? Do you see how it has tetrahedral shape to it? And so what we have here, I apologize guys, this is too tiny, but what we have here is this hydrogen and this hydrogen, they're in the same plane. And then we have this hydrogen right here. It's sticking out at you. So when I draw that hydrogen right here is this guy right there. The wedge implies that it's sticking out at you. So when you're looking at that on the screen, that hydrogen that's wedged is sticking out. And then that hydrogen that is dashed, this is a dashed bond right there, that means that hydrogen is sticking into the wall. All right? So there's 3-dimensional shape to the molecule. So we have the wedge and the dash bonds, and that's a tetrahedral shape. So how can that happen? Well, we need to figure out and remember hybridization states. This is going to really help us out. And why should you care how molecules look like? Why is that so important? And the reason is because it's a matter of life and death. It really is. When you go into the pharmaceutical industry or try to understand chemical biology, the shape of the molecule determines its function. If the molecule is not shaped properly, you get a disease or death. It's really that simple. And so, have you heard of mad cow disease? That's simply the proteins in the brain are not shaped properly, and the animal goes crazy and it dies. So the shape of molecules is critical to its function and how it operates. And that's why we're spending so much time at the beginning of the semester talking about the shape and being able to describe it and understand it, because it is so important. So if we take a look at that methane, and what is its hybridization state? What is the trick of that carbon atom there? What is its hybridization state? The trick is, how many electron groups are around that carbon? Well, that's a bond with the electrons. That's a group. That's a group, that's a group, and that's a group. So there's 4 electron groups around that carbon, and when you have 4 electron groups, that makes that sp3 hybridized. If we take a look at ammonia, what's the hybridization state of that nitrogen atom? Well, it has 1 group, 2, 3, 4. So that's sp3. What if we take a look at water? One, 2, 3, 4. That is also sp3 hybridized. So what does sp3 hybridized actually mean? If we take a look at the ground state of carbon again, we have 1s, and I don't care about 1s because it's the core electrons. What I care about, and you should care about, are the valence electrons. Those are the ones that do the chemistry. So we have a 2s and a 2p. Okay, and how many valence electrons do we have? We have 4 of them. So there's our ground state of carbon. When we want to hybridize carbon into an sp3 version, what's happening is these orbitals here, how are they represented? By math, by wave functions. Okay? So if we want to look at a hybridized state, what do we have to do? Just manipulate the math. So your carbon atom isn't like one day it's like I'm just in ground state and then sp3. It doesn't go back and forth. Okay? The carbon atom is just what it is. But we get to describe it in certain and different ways. And so now we want to look at it in a version of sp3 hybridized. So what does that mean? sp3 hybridized means we are going to take and generate 4 degenerate orbitals. Degenerate means what? Same energy level. So we're going to take and generate 4 sp3 hybridized orbitals. What does that really mean? We are taking 1 s orbital, which is this guy. That's an s orbital. And we're taking 3 p orbitals. 1, 2, 3. And we're going to mush them together using math and hybridize them to make 4 degenerate orbitals. So you see how there's a total of 4 orbitals over there at different energy levels? And now we're just going to say, we're going to manipulate it mathematically and make 4 of them the same energy level. And there's our electrons. You just start from left to right. So in that hybridized state, carbon now has 1, 2, 3, 4. That it can use those electrons now to form bonds. But how do those orbitals look like now? Well, we know an s orbital is spherical. And we know a p orbital is a dumbbell shape. When we hybridize those 2 together, we are going to get something that looks something like that. That would be a sp3 hybridized orbital. So it kind of looks like an s, kind of looks like a p. It's a hybrid. And so these 4 electrons right here that I've drawn on that carbon, are they going to orient itself around the carbon like this? No. It's going to orient around the carbon like this. in a tetrahedral geometry. And why is that the case? Well, you guys have been taught Würzburg theory, right? What's the bond angle between this bond and this bond? That's 90 degrees. When you compare a tetrahedral, what's the bond angle between the two? 109.5. You see it's larger? And why does that do that? Because the electrons within these bonds want to get as far away as possible from one another to reduce the electron repulsion. And so because of Würzburg theory, it says, hey, this is the best geometry to get those 4 electron groups far away from one another as possible. And so those 4 electrons around this carbon are in fact in orbitals in a tetrahedral geometry. So we would have something, we would have an electron there. We would have an orbital here. Then we would have a wedged orbital sticking out at you. And then you would have one sticking behind the board. And that's really hard to draw, right? Showing that three-dimensional shape to it. So you have to really understand that's what's happening when we're drawing these orbitals. 2 are in the same plane, up and there, then one's out at you, and then one's directly behind you. One thing though, because you are going to use these orbitals to draw molecules, and it gets very complicated very fast. And so to help with that, we are going to draw our carbons like this. I'm going to omit this little tiny lobe, just for convenience. So now our orbitals will look something like this. Okay, and we have our electrons in them like so. I'm just omitting that little tiny lobe. Is it still there? Heavens, yes. But we're just not going to draw it because it gets very messy. So these orbitals that I've drawn here, those are all sp3 hybridized orbitals. So now let's use this molecular theory here to draw methane. So we have carbon, and we know its hybridization state is sp3. And so that means we have 4 electrons there. And methane has what? It's CH4, so it has 4 hydrogens. So let's just draw 4 hydrogens. 1, 2, 3, 4. Each one of those comes with an electron. What orbital is the electron in on hydrogen? This electron right there. What orbital is it in? A 1s. Okay? So when we draw our carbon atom, let's draw our sp3 hybridized orbitals. And I'm going to put in those electrons. So you can see that I've accounted for those 4 electrons on the carbon. And what's the hybridization state of those orbitals? All 4 of them? They're sp3. Now the hydrogens are now going to come into play in a 1s. What does a 1s look like? It's just spherical. And so the hydrogen's going to come in, and that one hydrogen is going to bring one of its electrons. And so that bond right there, what we're describing here is a carbon bonded to hydrogen. So this red sphere is a hydrogen atom. That's what I'm representing by hydrogen. And do you see that red hydrogen and that blue sp3 hybridized orbital? There's overlap right here. That orbital overlap is represented by that covalent bond. So that covalent bond, we can describe it as such. We have a hydrogen in a 1s bonded to a carbon in a sp3 hybridized orbital. That's how that bond is forming, the interaction between the 1s and the sp3. Head to head, forming that covalent bond. Now we just do that 3 more times. Okay? So that hydrogen there, hydrogen, and a dashed hydrogen. So this molecule right here is representing that molecule right there. So if I draw a molecule for you, just some random molecule, and I say, hey, what orbitals are being used to form that covalent bond, you'll be able to tell me. Because you'll be able to look at the hybridization state of the carbon, and you'll be like, oh, that has to be a sp3 hybridized carbon because it has 4 groups. And then you do this whole analysis. So if we complicate things a little bit more now, what if we take a molecule and add another carbon? What if we take a look at ethene? All right, ethene looks like this. So if I draw that, or make that with my model here, that's what we get. Okay? Now take a look at the molecular geometry of that molecule. Do you see how it's flat? So there's a name for that. We have trigonal planar. So this carbon right here, what is its hybridization state? Okay, I already taught you the principal class. If I want to know the hybridization state of that carbon, what are we supposed to count? The electron groups. So if we do that, 1 group, 2 group, 3 group. So what is this hybridization state? sp2. That carbon is also sp2. Do you see the difference between the tetrahedral geometry and this geometry? The shape looks different. So what we have is that how many sp2 orbitals are we going to have? Well, let's figure it out. If we start with the 2s, and then we have a 2p, like that, and I said, and you figured out, that we have to hybridize that to a sp2, what does that look like? That is telling me I'm taking one of the s's and 2 of the p's. I'm going to take those 3 orbitals, and I'm going to hybridize them to a degenerate level. So we have 1, 2, 3. Those are my sp2 hybridized orbitals, all at the same energy level. But did I do anything with that p orbital? Did I hybridize it? No. So it just goes straight across and stays unaffected. We did not manipulate that mathematically. It just stays the same. Now, how many valence electrons does carbon have? 4. We just go from left to right. 1, 2, 3, 4. There's our 4 electrons in that hybridized sp2 carbon. So what does that look like? We'll take a look at the shape. Focus your attention right there. What's going on here? We're going to have a carbon atom with a sp2 hybridized orbital there, and a sp2 hybridized orbital there, and there. How do I know it's at those positions? Well, look at the molecule. We have that bond, and that carbon-carbon bond. Do you see how they're all in the same plane? Look at that. This bond and that bond, they're in the same plane. And then this carbon bonded to that carbon, it's all in that plane. So those orbitals have to be in that orientation. You can't have one orbital pointing this way and just all wherever you want it. The molecule looks like this. Okay, so that's our carbon. But where's that p orbital? Where's this p orbital going to show up? Well, that p orbital is going to be perpendicular to those 3 sp2 hybridized orbitals. What do I mean by that? If if I take this model and flip it this way, you see this bond, and this bond, they're all in the same plane. So where's the p orbitals? Perpendicular to that, which is 90 degrees. So the p orbital is right here and below. Above and below, because that's what p orbitals look like, a complete dumbbell. So it's all above and below. Perpendicular. So when I try to draw that, it's hard to do, but we do the best that we can. That is perpendicular to those three green orbitals. And so this electron is going to go there. We have different phases. And then I'm going to account for this one. I'll put it right there, this one right there, and that one right here. Okay? So now I've looked at the electronics of just one of the carbons. But how many does ethene have? It has 2 carbons that we have to account for. So let's focus our attention on that one. So we'll put the carbon right there. It also is sp2 hybridized. So it's going to have an orbital there, there, and there. It's going to come with the same amount of electrons as the other one. So we'll have our sp2 hybridized orbitals and our p orbital. Like so. Let's account for this one. Boom. We'll put it there, there, and there. Now what did I just do right there? There's orbital overlap right there. I just created a bond. So what we've done is created this carbon-carbon bond right there. And then we have the p orbital that we haven't accounted for yet. Okay? So let's tack on our hydrogens for this next part. So how many hydrogens are we going to have in ethene? 4. And so those are going to come and attach here with an electron, electron. Okay, so those represent those 4 hydrogens right there. What type of what orbitals are used to form that bond right there? You could say a hydrogen 1s forming a bond with a carbon sp2 hybridized orbital. Those are the orbitals that are used to form that bond. And that bond is also called a sigma bond. And sigma bonds are simply when you take a look at the atom and you look at the orbitals shown there. Do you see how they overlap head to head? Now that's going to make a little bit more sense once I show you what a p bond looks like, or a pi bond. But that is a sigma bond. This p orbital and this p orbital, they can interact with one another above this axis right here. So compare and contrast. Do you see these sp2 hybridized orbitals right there? Do you see how they're end to end, forming a nice tight sigma bond? But when you look at the pi bonds, they're above and below the atoms. So if I hold this like this, where's those 2 p orbitals? Above and below. And they're interacting above these atoms. And so that is called a pi bond. That's a pi bond right there. And I'm going to represent it, that double bond right there, like that. So there's our pi bond. What orbitals, how would you describe that orange bond? What orbitals are used to form that orange bond? That would be a carbon, p, forming a bond with a p orbital. How would I describe this blue bond right there? That would be a carbon sp2 forming a bond with a carbon sp2. Any questions up to this point? No questions. Okay. Let's take a look at another molecule. Let's take a look at ethine. That would be a carbon, triple bond, one hydrogen. What is the hybridization state of that carbon? Raise your hand. What do you think? SP2? Yeah. SP. It's the same principle that we just learned. Nothing changes. I'm interested in that carbon. How many electron groups are around it? 1, 2. So now we have 2 electron groups. So that makes that carbon SP. Take a look at it. Look at the molecular shape and the geometry of the ethine molecule. What's the relationship? How would you describe this molecule? Tetrahedral, trigonal planar? It's linear. That's a linear molecule. What's the bond angle then? 180 degrees. And so we need those orbitals to be 180 degrees from one another. So we need a carbon that has a sp and an sp orbital just like that. 180 degrees from one another. So what is the ground state of carbon? 2s and then 2p. And what did we want to hybridize that to? sp. So what does that mean? 1s, 1p. Hybridized. What have we done? Did we do anything with those? Nope. So those just come straight across. And we have p orbitals. How many valence electrons does carbon have? 4. Okay. So when we take a look now, let's focus our attention on the sigma bonds. So this electron right here is going to go there. That electron will go there. And what's going to happen? Well, let's take the second carbon. There's our sp. There's our sp. That second carbon comes with 4 electrons. 2 of them are going to be in the sp. So we'll put it there and there. Do you see what we've just done there? We formed an orbital overlap. So now we have created a carbon-carbon bond. And since that's head-to-head, or end-to-end, however you want to say it, that would be a sigma bond. And so that's between what? A carbon sp, carbon sp. Let's check on our hydrogens before we tackle the pi bonds. So 2 hydrogens. So let's bring in a hydrogen and bring in another hydrogen. Okay? So we've just tacked on our hydrogens here. And what orbitals are used to form that bond? A hydrogen 1s and a carbon sp to form that orange bond with carbon. Now we have, for this carbon right here, we have to account for 2 of the p orbitals. And let's draw it in blue. So our first p orbital is going to be right there. We'll put the electron there. Well, we have accounted for that one. Let's do the same thing for the second carbon. Okay. So we've accounted for 2 electrons, or 1 electron each. Now, let's focus our attention on this one. Where's that one going to be? Well, let's first take a look at our molecule here. So that blue p orbital, where is it with respect to this molecule? It's above and below the carbon. Okay, completely perpendicular to the sigma bond. Now, where do you think the purple is going, the other p orbital is going to go? Perpendicular to this p orbital. So if it's above and below, where's perpendicular? Towards you and behind me. So we have another p orbital that's perpendicular, and that gets really difficult to draw on a piece of paper. But we do the best that we can, and so we would draw something like this. We would have an electron there, and then we would have it here and here, the electron there. So now we have with the purple pi overlap, which we can represent like that. And then we also have the blue p orbitals that have overlap. And it's getting nice and messy here, represented with that blue bond right there. So ethyne, between the two carbons, we have one sigma bond. And that sigma bond is created from what? Two carbons that are sp hybridized. And then we have two pi bonds, represented in that color code. And so your textbook has, I will fully admit that they have better drawings, computer-generated drawings that will make, if that doesn't make sense to you now, your textbook has some prettier drawings to demonstrate that. But that's what's going on. We have all these p orbitals and hybridized orbitals all just in the same space forming bonds. And we need to be able to look at that and look at any molecule and figure out the orbitals that are used. Okay? Any questions up to this point? Yeah. Now remember, you guys are going to have access to all these notes. Okay? So there's no need for people to come up at the end of class and say, "Can I take a quick picture?" My answer is no. No. You can just wait until they're uploaded, okay? I'm just trying to make life easy for everyone involved. Okay. So do you guys think you can put this into practice? Okay, what class started at 3? When does it end? 4:15? Can you do what orbitals? Just answer the same questions that I've been teaching this whole time. What's the hybridization state? What orbitals are used? So we have 3 different types of bonds in this molecule. What orbitals are used to form those bonds? Go, discuss, work with someone, draw it out. Let's see what you come up with.